If you are new to the channel, then subscribe the channel and press the bell icon for further notification. Okay students, welcome you to lecture 31 of this switchgear protection series. So today we are going to start percentage bias differential protection relay. Until last lecture we have seen simple differential relay. So we will see some terms that is known as throw fault stability or stability ratio. What is this in simple differential relay, and why the percentage bias differential relay came and how we will implement that one. Now the idea for throw fault or external fault current in simple differential relay that the secondary current for both the cities for external fault or throw fault, it should be same in magnitude and phase angle, and the spill current is zero. That was the basic idea for simple differential protection scheme. But as I was discussing in that lecture, there will be always a CT ratio, error and phase angle error, due to which there will be always a difference between these two currents, and there will be always a presence of spill current. And this spill current and this error increases. This increases with the rise of throw fault currents. If you keep on increasing your throw fault current or external fault current, if it is very high, then this error gets magnifying. More and more errors will come, and due to which your spill current will increases. We have already seen this error comes because due to city saturation. It will cross the saturation curve where it is not directly proportional. Your I you are giving that 80 ampere turn you are providing through axis, and the flux you are getting will not be directly proportional. So whatever current you give in the primary, proportionate secondary current you will not get it. So there will be always error created, and that error keeps on increasing as your external fault current increases. So due to which your spill current is also increases, and there may be a time comes when your external fault current will be crossing that spill current, will overtake that spill current, and the relay will starts operating, or the trip circuit will be initiated and it will be tripped, which is a mal operation for us, because for differential protection external fault we don't want to interfere with the external fault. We are only concerned about the internal fault also. This scheme should operate only for internal faults. So if you see the characteristics of a simple impedance, simple differential protection scheme, so this is my axis, and what is this axis? This is spill current, the current that is passing through the branch, that is middle branch, you can see, and this current is your external fault current. You can see here, this is external field current or throw fault current. This is your throw fault current or external fault current, and this is your spill current. So you have both these axes now. Okay, so you have a minimum value you have set, that is I plug setting you have given. So above which it will be always a trip, and below which it will be a restrain. So what will be the external fault characteristics? That means how your spill current will change if your external fault or throw fault current increases. So you can see as your throw fault current increases, it starts gradually increasing your external fault, due to which the spill current starts increasing by this way. So this starts gradually increasing as your throw fault current increases. So up to a certain point it will come when it will cross your plug setting that you have given. So at that beyond this point the relay will trip for external fault. You can see it is going to this trip zone. So relay will trip. So up to this much, the maximum external fault current that it can hold, suppose I gave it a name of I step, that is I stability. So when a fault current crosses the I step, the spill current crosses the I plug setting, hence the relay trip for the external fault currents. Now this is not desirable for me. I want this not to happen, but due to this error it is coming. So I have defined a ratio which is known as stability ratio, which is maximum throw fault current beyond which the scheme mal operates. Mal operates means it trips, and the minimum internal current that is required for tripping. The ratio between these two, that is IF maximum external divided by IF minimum internal. What is the value of IF maximum external here? Here it is I step, and minimum, that is the I plug setting that you have given. So that will be your minimum fault current for which it should trip. So you can see higher the stability ratio, the better the system to differentiate between the internal and external fault. So if your stability ratio is very high, that means this IF max will be very high. If it is very high, then the graph will be more flatter graph. It will cross in this way, so you will get a maximum fault current for which it will not trip, which is desirable for me. I want to make it as much as big as possible so that for any external fault it should not trip. That is the idea. So your stability ratio will be, if it is better, then that means, what is it means? It means system can better differentiate between which one is internal fault and which one is your external fault. The stability ratio can be improved by improving the match between the cities. If both the cities are very identical to each other, then it is highly likely that the errors caused in first city and the error caused by the second city will be in same line, so that the difference between that is same. But in practice it is tough, because you will be seeing in transformer protection the both side city ratios are different, because transformer there is a voltage ratio, so both side currents will change, so accordingly your city ratios will also change, due to which these cities will not be identical, and the error caused in one city is different from error caused in different city. So that's why there will be always a spill current. Now there is another way of improving your stability ratio, and that's the idea of the stability ratio, how to improve this one. One was matching between the cities, but it is not possible, as I was discussing. So the another idea is percentage bias differential relay. So the idea is simple to give some sort of restraining torque, that is holding up the relay. This torque will not operate, it will hold up, it will act reverse to your operating torque. So it will hold the relay to operate in case of a throw fault current, in case of an external fault. Whenever there is external fault, let's try to give a restraining torque and make it proportional to the external fault. As your external fault increases, this torque also increases. So more and more holding it back. So if it is holding its back, means the disc will not rotate, the relay will not trip. So that is the idea. So how we will implement this one? This is the idea. The idea is to give a restraining torque, that is a holding torque, which is proportional to your throw fault current, so that the stability ratio of the simple differential relay can be improved. This is the basic idea on which it is working. So how we will do it? Let's see the diagram first. So if you see the diagram, this is the equipment which is under protection. There is a source here, and the current is flowing in this direction. So you can see both the cities, you can see the dot polarities, as I have already discussed the dot polarities. Here I have not given, so let me give it here. So if it is leaving out of here, so it should enter through this, so another dot will be here. So this dot, you have to be very careful, because you have to create this path, you have to create this sort of path. Either current should flow and then coming back to this side, or another thing, current can go this side and then back to this side. That also can be done if you do the proper city connection. Both ways it is possible. So the idea is, here you can see what is the idea. They have put in two coils of NR/2, NR/2, which are known as restraining coil, through which this current flows, I2 and I1. So if there is an external fault outside, so it is likely that your I2 will also increase, I1 will also increase. So the torque produced by these two coils will also increase, so which will hold it back. So how much it will hold it back, what is the property and what is the derivation of this one? Now if you see the derivation, what is your let's see the properties, see some properties of this percentage bias differential relay. So what is the ampere turn here? It is turned into ampere. What is the turn? This is NR/2. NR is the restraining coil number of turns, that is divided by 2 into I1 current is flowing through this, and second one is NR/2 I2. This is left side restraining coil, how much ampere turn it is working, and in the right side restraining torque, how much ampere turn it is creating. So what is the total ampere turn in the restraining coil? If you add left hand side and right hand side, so this is the total amount of ampere turn that is working, acting on the restraining coil. So what is the torque produced by the restraining coil? We know torque is directly proportional to, you can recall my earlier lectures, that is before IIDMT initial lectures, where we have discussed T is equal to directly proportional to phi 1, phi 2 sin alpha. What is phi 1, phi 2? This is created due to current, that is 80 ampere turn. So torque is proportional to ampere turn whole square. So you can say torque is proportional to your 80 whole square. So this is written as m into something, that is proportionality constant we have used. Okay, so total restraining torque will be this plus spring torque. Spring torque will work once it starts working, then it will come to bring it back to the original position. That's it. So total operating torque is, this is restraining torque. And what is operating torque? You see the drawing, your operating current remains the same. This is I1 is coming I2. So what is the current flowing through this? The spill current is I1 minus I2. So this is the operating torque. So it remains same. This is the operating coil. So the torque produced by the operating coil is this one, M into N0 I1 minus I2. So now relay will be at the verge of operation, that is supposed to operate. At what point it will start operating? When your operating torque is equal to restraining torque. Here we have neglect the spring torque, because it will come when it starts operating to bring it back. So, and it is very small with comparison to your operating torque and restraining torque. So you can neglect this one anytime, because this is very small. This idea is to bring the needle back to its original position once its job is done. So it is very small torque. Once your operating torque restraining torque comes into picture, this becomes negligible. So you can neglect this one. So if you neglect this one, your equation becomes, this is the main equation you can think of. This is your operating torque, or this is your, you can say, spill current, and this is your throw fault current also, you can say. Because if you do it, I1 is directly I1, you can think of I1 is IF fault current, some portion of fault current. Forget about CT ratio, you think 1:1, just I am giving the idea. So it is also giving IF, I1 is also giving IF, I2 external fault. Both there is external fault, IF external, then I1 will also measure external, I2 will also take care of that external. So IF plus IF divided by 2, that is IF. So this portion you can say it is throw fault current. This is throw fault current, and this is spill current. So you can think of these two different set of currents. One is in operating coil, this is in operating, and this is in restraining. So if you see, now you can bring the control spring back, so the complete equation will look like this. If you like the video, then press the like button, and please give your valuable comments in the comment section.